Hi everyone, welcome back to Introduction to Artificial Intelligence and Machine Learning. In the previous session, we give an overview and introduction on the major types of machine learning algorithms and their corresponding use cases. In this session, we will focus on supervised learning and classification algorithms. As we know, the supervised machine learning algorithm can be broadly classified into regression and classification algorithms. In this session, we will first talk about classification algorithms. So, what is classification? The classification algorithm is a supervised learning technique that is used to identify the categories of new observations on the basis of training data. In classification, a program learns from a given dataset or observation and then classifies new observation into a number of classes or groups, such as yes or no, 0 or 1, spam or not spam, cat or dog, etc. Classes can be called as targets or labels or categories. The output variable of classification is a category, not a value, such as green or blue, fruit or animals, etc. Since the classification algorithm is a supervised learning technique, therefore, it takes label input data, which means it contains input with the corresponding output in order to train the classification model. The main goal of the classification algorithm is to identify the category of a given dataset, and these algorithms are mainly used to predict the outputs for the categorical data. Classification algorithm can be better understood using this diagram. In the below diagram, there are two classes, Class A and Class B. These classes have features that are similar to each other and dissimilar to other classes. The algorithm which implements the classification on a dataset is known as a classifier. There are two types of classifications. If the classification problem has only two possible outcomes, then it is called as binary classifier. Examples are yes or no, male or female, cat or dog, spam or not spam, etc. If a classification problem has more than two outcomes, then it is called as multi-class classifier. Some examples are classification of types of crops, classification of types of music. Here, classification algorithms can be further divided into the two categories, linear models and nonlinear models. Some typical examples for nonlinear models such as logistic regression, support vector machine. And for nonlinear models, we have k-nearest neighbors, kernel support vector machine, NaiveBased, decision trees, and random forest. In this session, we will introduce some of the popular algorithms, including simple theories and their applications. Logistic regression is used for classification. Logistic regression results in the linear decision boundaries. It uses a logistic function to model the output variable. The dependent variable is dichotomous in nature. That means there could only be two possible classes. Either a student was admitted or not based on their exam scores. As a consequence, this technique is used while dealing with binary data. Second is called support vector machines. Support vector machines find the boundaries that separate classes by as wide as margin as possible. When the two classes can't be clearly separated, the algorithm finds the best boundary that they can. When output variables are numeric, logistic regression and support vector machines should be the first try for classification. These models are easy to implement, their parameters are easy to tune, and their performance are also pretty good. To separate the two classes of data points, there are many possible hyperplanes that could be chosen. Our objective is to find a plane that has the maximum margin. That is, the maximum distance between data points of both classes. Maximizing the margin distance provides some reinforcement so that future data points can be classified with more confidence. The next algorithm for classification is called k-nearest neighbor. K-nearest neighbor algorithms are interesting and simplest of all machine learning algorithms. The KNN algorithm assumes that similar things exist in close proximities. In other words, similar things are near to each other. First of all, this algorithm will memorize the training dataset with their corresponding label, and then to forecast the label of any new input data points based on the label of its closest neighbors in the training set. Next, we will talk about NaiveBased Classifier. All NaiveBased Classifier assumes that the value of a particular feature is independent of the value of other features, given the output variables, and that makes NaiveBased algorithms extremely fast compared to other classification algorithms. It works on Bayes' theorem of probabilities to predict the class of unknown datasets. For example, a fruit may be considered to be an apple if it is red, round shape, and about 3 inches in diameter. Even if these features depend on each other or upon the existence of the other features, all of these properties independently contribute to the probability that this fruit is an apple, and that is why it is known as naive. Naive-based model is easy to build and particularly useful for very large datasets. Along with simplicities, naive-based is known to outperform even highly sophisticated classification methods. Next, we'll talk about decision tree. Decision tree is a supervised machine learning algorithm that uses a set of rules to make decisions, similarly to how humans make decisions. There are many variants of decision trees, but they all do the same thing: subdivide the feature space into regions with mostly the same label. The intuition behind decision tree is that you use the dataset features to create yes or no questions, and continually split the dataset until you isolate all data points belonging to each classes. With this process, you are organizing the data in a tree structure. Let's look at this example. Here we have a dataset of many people's data, and we have their income and age. And our objective is to predict whether these people will attend Burning Man or not. So those in yellow color attended Burning Man, and those in blue triangles are those did not attend. So how can we draw the boundaries using decision trees? We start to ask questions. Whether a person's income is less than 61,000. If yes, then these people will not attend Burning Man. If no, then we will ask a second question. Is these people younger than age 27? If yes, then they probably not attend Burning Man. If no, we ask next question. Are they younger than age 38? If yes, they will attend Burning Man. If no, they didn't attend Burning Man. So based on this decision tree, we can come up with this conclusion that who will attend Burning Man. That will be those people who are earning more than 61,000 and in the age between 27 and 38. Finally, we are going to talk about random forest. Random forest algorithm, like its name implies, consists of a large number of individual decision trees that operate as an ensemble. Each individual tree in the random forest spits out a class prediction, and the class with the most votes becomes our model's final prediction, as shown in the figure. The fundamental concept between random forests is a simple but powerful one: the wisdom of clouds. In data science speak, the reason that the random forest model works so well is a large number of relatively uncorrelated models or decision trees operating as a committee will outperform any of the individual decision tree. The reason for this wonderful effect is that the trees protect each other from their individual errors. While some trees may be wrong, many other trees will be right. So as a group, the trees are able to move on in the correct direction. After talking about different classification algorithms, now we are going to talk about how are we going to evaluate a classification model, because this is equally important as building it. We are creating model to perform on new, previously unseen data. Hence, a thorough and versatile evaluation is required to create a robust model. When it comes to classification models, evaluation process gets somewhat tricky. In the following section, I will try to provide a detailed guide on how to evaluate a classification model, including a range of different metrics. Basically, there are four. We have classification accuracy, confusion matrix, precision and recall, ROC curve, and AUC. And we are going to introduce each one of them. The first important evaluation metric is called accuracy. Classification accuracy shows how many of the predictions are correct. In most cases, it represents how good a model is, but there are some cases in which accuracy is simply not enough. For example, 93% means that we correctly predict 93 out of 100 samples. It seems acceptable without knowing the details of the task. Assuming we are creating a model to perform binary classification on a dataset with unbalanced data distribution. While 93 of data points are in class A and 7% in class B. Let's say you have a model that predicts all samples are class A, and the accuracy of your model is 93%. What if it is critical to detect class B? Because in some cases, we care more about the minority class, such as cancer detection. In these cases, we need other metrics in order to evaluate our classification model. A confusion matrix is not a metric to evaluate the model, but it provides insight into the prediction. It is important to learn confusion matrix in order to comprehend other classification metrics such as precision and recall. Confusion matrix goes deeper than classification accuracy by showing the correct and incorrect predictions on each class. In case of a binary classification task, A confusion matrix is a 2x2 matrix. If there were 3 different classes, it is a 3x3 matrix, and so on. In order to understand confusion matrix, we need to take a look at different terminologies. Let's assume in a binary classification example, class A is positive and class B is negative. Here we have 4 terms. True positive means predicting positive class as positive, and this is okay. And true negative is predicting negative class as negative. This is okay as well. False positive means the model predict negative class as positive. This is not okay. And false negative means the model predict positive class as negative. This is also not acceptable. The desired outcome is that the prediction and the actual class are the same. Let's go one step further. We are going to talk about precisions and recall. Precision and recall matrix takes the classification accuracy one step further and allows us to get a more specific understanding of model evaluation. Which one to prefer depends on the task and what we aim to achieve. The focus of precision is on positive prediction. It indicates how many positive predictions are true. The focus of recall is the actual positive classes. It indicates how many of the positive classes the model is able to predict correctly. We cannot try to maximize both precisions and recall because there is always a trade-off between them. Increasing precision decreases recall, and vice versa. We can aim to maximize precision or recall depending on the task. If we are going to build an email spam detection model, we try to maximize precision because we want to be correct when an email is detected as spam. We do not want to label a normal email as spam, which is false positive. On the other hand, for a cancer detection task, we need to maximize recall because we want to detect positive class, that means cancer, as much as possible. Finally, we are going to talk about ROC curve. ROC curve is called Receiver Operating Characteristic Curve, and AUC means area under the curve. These two measures are best explained with a logistic regression example. Logistic regression gives the probabilities of a sample to be positive. Then, we set a threshold value for this probability to distinguish positive and negative classes. If the probability is higher than the threshold value, the sample is classified as positive. Therefore, different threshold value result in some sample to be classified differently, which in turn change precision and recall metrics. ROC curve summarizes the performance of the model at different threshold values by combining confusion metrics at all threshold values. The y-axis of ROC curve is called the true positive rate, and the x-axis of the ROC curve is the false positive rate. Our aim is to increase the true positive rate while keeping the false positive rate low. Therefore, the larger the area under the ROC curve, the better the model is. To sum up the evaluation metrics, no free lunch theorem applies here too. There is not an optimal and easy to find choice for all tasks. We need to clearly define the requirements and choose a metric based on these requirements.